So today we are going to discuss about process synchronization. For the process synchronization, before we shall proceed it by discussing producer consumer problem. The necessity of discussing this producer consumer problem is to understand the problems faced during the process coordination. Say there are two kind of process. One is independent process. Next is cooperating process. Independent process which cannot be affected by any process, and even that process won't affect any other process during the course of execution. That is, it won't try to communicate with other process, and even it won't let other to communicate with itself, right? The second category of the process is called cooperating process. Yes, the cooperating process have a ability to communicate with other process, and as well which can be communicated by other process, and even it will go for communicate with other process. So we can say the cooperating process will disturb other process, and even it will be disturbed by other process. What is the purpose of allowing the process to communicate with each other? Say in multiprocessor environment, there are many occasions where we need process need to be communicated with each other. What is process? Ultimately, a program can be decomposed into number of small tasks, and we will call it as a process, and which will be executed by an CPU execution unit. So during course of such division and making it as a process and to be allowed to execute it by an execution unit, some sort of a time which needs to be share the information to its process which belongs to the same program. Okay, a program, and which is divided into number of. So this is P1, this is P2 of the same program, and P3, so on. So at some occasion, the output of P1 needs P2, and P2 needs data from P3. So in such occasion, we need to allow the process to communicate. So there are two categories. Upon if it is required, we can mark the particular process, or the operating system will mark the process as independent process. So there won't be no possibility of communicating with other process. The second category of the cooperating processes, which will go for to share the informations. Now, what kind of precautions have to be taken if we allow the process cooperating with each other? So we will discuss it with a simple problem. We have a producer consumer problem with bounded buffer, with unbounded buffer, and reader writer problem, right? So we will discuss these problems one after another, so that we will find the necessity of process synchronization and how we can achieve the process synchronization. And before going into even this, we should discuss circular queue. Okay, I hope you all aware of what is queue is. Queue is a first in, first out data structure. And now we are going to deal with circular queue. It is nothing but the queue, normally the queue will be represented in this form, right? This is 0, 1, 2, then n. So this is the first, right? So the item will be taken out from this, and as soon as the items are entering, and which will go through this way, and which can be placed at the front. Okay, this is front and the rear end. From the rear end, it keeps on entering the data, right? Now, for the sake of to utilize the queue efficiently, say for example, if you keep the queue in this way, it is 0, 1 till n. Say there will be we are going to have a pointer here, right? As soon as we have occupied this, we will move the pointer here. So upon, if the pointer have reached at this point, right, we may say the queue is full. Now you have removed an item. Okay, so now the very first item is here. The very first item is here. Now this portion is free, and a pointer which is pointing to the last item says the pointer is reached last item, so there is no space. So to make a room at this place, because the newly entered item into the queue cannot be placed at this place, because the item which is entered into the queue very first have to occupy at this place, and it has been removed. So the next item should be placed at this, right? So now in such case you need to shift it, because you need to make a room at this place for new items. So if you doing so, see, you need to switch all the items towards front one place, right? So it's a very complex task. Say if it is of a lakhs of number, right, then it will be the time complexity of to achieve this will be n minus 1. You need an iteration for almost n time, right? So to overcome from that overhead, to come out of that overhead, we can use circular queue. It is like you have bent and front and rear end are joined together. So let you assume 0, 1, 2, 3, 4, 5, 6. So here totally there are 7 items can be placed, right? The maximum size of this queue is 7 items, starting from 0, the very first one, till it can 6. So 7 items can be placed. The maximum size of the circular queue is 7. Now initially there will be 2 pointer associated with this, in and out. In points to the front, the item which is placed, right, and which points which allow us to whether we do have a space for new item, whether is it full or not, which can be identified by examining these 2 pointers, in and out, right? So now in is used to, as soon as we are occupying or we are placing new item into it, the in pointer will be, say, as soon as you have done it, the in pointer will point to this. So likewise we are going to move the pointer one after another. Say let you assume the pointer is at this place, in, right? Now out is here. What is out? This out is for which will give a clue about at which item can be removed. The item which can be removed, or you can say the item which is entered into this queue first, is pointed out by out. So now say if we wish to remove an item, yes, this item can be removed because the item placed at this area is entered into the queue very first. So this can be consumed or retrieved from this queue first. And as soon as you have retrieved, the out pointer will be moved to the next, right? Then again you have removed one more item, then out is here. Now in is here. Say if you wish to add few more items, yes, as soon as you have added one more item, this in pointer can be placed over here, the next here, then after this you can move even over here, right? So now for to achieve such to utilize this queue in this manner, you need to write a program accordingly. That is moving a pointer of upon reaching 6. If next is free, you need to test whether the out pointer is at this place. In such case, it is full. If this is free, that is out is pointing other than 0, which means that you have removed some item so that you do have a places or a free area in your queue, so that the pointer can be moved from 6 to 0 furthermore, so that the program knows that you do have a place to accommodate new items. So this is what circular queue is. And with the help of the circular queue, we are going to see how a producer consumer problem will allow to know about what the problem may occur if we allow a program or the operating system to share a space, right?
Sir, is there an explanation mark before n in the while loop of producer?
While loop of producer,
So like you have written no n plus 1 divided by buffer size. So is there something before n?
before n.
Is there like while and you have given the brackets and
Yeah,
then is there something before n like it's n plus 1 divided by buffer size or something some symbol is also
it
there?
is okay. This symbol, it is percentage. It is percentage.
I was asking what's in the bracket of buffer like in below you have written buffer n.
Bracket of buffer, where
Like buffer bracket n is equal to next product so that's n.
it is in in.
Acha, okay.
It is in. There is no n in it. It is in.
Okay.
So first, let me see what is producer consumer problem is. Let you assume a scenario. Producers are the task assigned for them is they need to produce an item, and consumers are allowed to consume it. Okay. Now, let you assume a situation. They do have a space. Okay, and producers, as soon as they have produced, their task is to keep the produced item into the dedicated place. Okay, let you assume it is a dedicated area for it, and consumers are allowed to pick up the items from the place where the producers are keeping. So it is a shared area, right? So this is an area from where the producers are going to produce and keep. And this is the same place from where the consumers are going to consume. That is to pick an item so that they can consume it. And now it may be a bounded buffer, right? We call it, this is a buffer. This is an area from where both are utilizing. And the example which or the problem which we are going to discuss is it is bounded buffer, that is size is fixed, right? So let you assume this can hold approx 10 items, not more than that. Exactly, this has an capacity of holding 10 items. Now producer and consumer both should go in synchronized way, right? What is synchronization? As soon as someone is ready to give an item, right, and the receiver should ready to receive it, right? If there is no space to keep it, if they find there is a space that they can't go in synchronized mode, because as soon as the producer is produced, they have got a space so that they can keep it, right? And the producer can come if they find the place is having some items so that they can consume it. Okay, and the handshaking is an example for synchronization, right? So where we do not have such provision to keep, then you need to go in synchronized way. That is, as soon as I'm ready to give and the person who is ready to receive it, they should be ready, right? Otherwise I may throw somewhere and it may gone in vain. That is, it may last at somewhere, right? So here, but we do have a bounded area, bounded buffer area, so that they are going to keep their items and consumers are going to consume items from this area. Now, we have simulated this with this program. Producer is a code, a program, and which is going to produce. Okay, but here the condition is that which needs to obviously check the size, whether is this has exceeded. They cannot produce items more than 10, right? But this code has, if the buffer size is 10, maximum utilization is 9. That is buffer size minus 1. They cannot utilize exactly the entire buffer size. Right? This code is written such a way that if the buffer size is of a 10, the producer can produce only 9 items maximum. They cannot utilize it completely, right? Now come to the code. Say while true, this loop is going to be true at all the time. We have written true, or either you can keep it as a 1, which says that always true. Now we do have a code here, right? That is a code as we are going to simulate only this, how it is going to produce and consumes and how to utilize the buffer area. This area we can have how you can process the data, right? So I left it as a free. We are not worried about how it can be produced and how it can be utilized. So now come into, before going to place an item into the buffer area, you need to check that whether this is plus, not int. Okay, this is in plus 1. You are going to check that whether the buffer size is full. According to our implementation, whether is it has reached exact buffer size minus 1. If it has reached, say I have put a semicolon. Do you know what happens if a while loop has a semicolon? Do anyone know it? But in any program, I hope you find that the while loop do not ends with semicolon. Because if it has a body, this will go for, upon this condition is true, which will go for to execute the body of the while loop. But here we do not have a body. This line is written very cleverly to keep the execution, right, in this line itself if this condition is true. If the condition is true, this execution is, the execution won't go beyond this line. Only upon finding this condition is fails, then the execution will come to it. Okay, so that's why we have kept a semicolon. In book you can find that by putting a semicolon here, do nothing, which means that it is not going to do anything. We are not going to have any body for this while loop, right? This while loop is made specially for to keep the execution busy in executing this while loop, right? Because this condition is satisfied. Say if this condition is satisfied, which means that you do not have a space in the buffer, it is full, that is it has reached buffer size minus 1, right? So we are making it busy with executing this line. Then if it has a space, then obviously this condition is going to be false, then which comes into buffer of in. The current in, let you assume that initially it is 0. If it is 0, buffer of 0 is going to have next item which is produced, which means that the item which is produced by this producer is placed in buffer of 0. Then the in pointer will be increased by 1, right? So let you assume 0, right? And in and out both are pointing to this place initially. Let you assume both are pointing to this place initially. As we found, both are 0. So in 0 plus 1 by buffer size, let you assume it is 5. So 1 modulo division 5, you will get 1. So out to 0. So it is false. So it comes out and it is going to place the item which is produced in the this place. Right? Let you assume an item has placed. Then in next step, int plus 1. In equal to, in is going to be updated by in plus 1 modulo division buffer size. So now this in is going to point 1. Right? At this place. That means the value of in is 1. Right? And it is pointing to the place where a next item can be placed. It is free, right? And now out is pointing to the item which is placed here. Say if next item was produced, then the next item will be placed here, then the in pointer will be moved to at this place, which will point to the next free position, so that in the next iteration a new item was produced so that it can keep at this place, right? Then at the last, say it has placed 4 items. Now the value of I is, right, here, right, in, let you assume in is 3. In is 3, right? The pointer in is 3. So 3 plus 1, 4, and I said that the buffer size is 5, right? So we have got 4. Out is in this place, so it is wrong, so that it can. So the item is going to be placed over here. Then now the in pointer will move into this place. So now the value of in is 4. Say this place is free, which means that even if you do have one more item, it can be placed. But this programmers have a constraint that it can utilize only n minus 1 of the buffer size. Buffer size minus 1. So now, even if it is pointing to the free space, it cannot accommodate a new item. Say it is 4. So 4 plus 1 is 5. 5 by buffer size is 5. Modulo division. The remainder is 0. And out is pointing to 0. So 0 equal to 0 is true. And it is going to keep the execution busy in this while loop. It will keep on executing until this condition become false. So when this condition become false, now only the opportunity is if the out pointer is moved to the next place, right? So is it clear, this producer code? And we will see how a consumer works. Now the consumer work is very narrow. It is going to consume item, that is, it is going to pick item from the buffer. Whether in equal to out, is it equal? At this example, what we are discussing here, it is in and out is not equal, because in have moved by placing one after another items. Then right now the value of in is 4, and the out is pointing to 0, very first item, the item which can be consumed. It fails. Even if it is 0, there is no item. So the consumer program won't allow to consume it, because there is no item. How it can be consumed? So this is going to keep the execution busy in this line. Say a semicolon is placed here, which means that if this condition is true, the execution is going to be here, right? It won't go further. It is not going to reach the next line. Only upon finding if this condition is fails, that is, if the value of in and out is different, it is not same, then which may come out. So as per our assumption here, the value of in is 4 and out is 0, so that it is moved. Item consumed is buffer of out. What is the out value? It is 0. So this item will be saved here, which means that it is consumed. Now out needs to be moved one step further towards the next item. Out equal to out plus 1 buffer size. So out is 0 plus 1, 1 by 5 modulo division, the remainder is 1. Now this out is moved to at this place, right? Now if you execute this code, now 4 plus 1, 5, it is 0, but the value of out is 1, so that it allows to produce it, because it is going to utilize and it has moved, so that the next item can be placed over here. Now 4 plus 1 is 5, 5 by buffer size, 5 by 5, remainder is 0. Now in becomes 0, right? So the in is pointing to this after placing a new item, and in is going to point this. So this is how this is going to utilize this, right? So now what is the problem may occur in this? First of all, the problem is that we wanted to make this program to utilize the complete buffer size. For the purpose of to utilize, as I said, that this is going to use only the buffer size minus 1. It can utilize only, though the buffer size is of a 10, it can utilize only 9. It can accommodate only 9 items. Say if you want to change this program to utilize the complete buffer size, we may introduce counter. Okay. And this counter is going to tell us how many items are having it in R, buffer, right? So with the help of this buffer, the producer can find that whether 10 item has produced and 10 items are placed, and upon checking here you can check that whether the counter is out. If it is instead of this, right, we can check whether the counter has reached the buffer size. Right, counter has reached buffer size. So what exactly we are checking here, whether the counter is of a buffer size. If it is true, it will keep the execution busy so that it won't allow to go furthermore. If it fails, what does that mean? Counter is not reached the buffer size so that it can place the produced item. Right, the same way here. Right, the counter, right, here we are going to check that whether the counter is 0. If the counter is 0, there is no item, so that the consumer program won't allow to consume it because there is no item. How it can be consumed? Right? A very simple strategy. Just I have changed here counter as a buffer size. Before placing an item, I need to check whether the counter has reached the maximum buffer size. If it is buffer size, which won't allow to place it. And here we are going to test whether the counter is value is 0. Upon finding it is 0, there is no item, so it cannot be consumed. Right? So appropriately we need to, as soon as an item is consumed, you need to decrement the counter value. As soon as you have placed a new item into the buffer, you need to increase the counter value. Is that clear? Is that clear?
Yes, sir.
Okay. Just two changes. I have introduced a counter for the purpose of to utilize the buffer completely, because the earlier version of code have a bug, or you can say a limitation. The buffer is not utilized completely. So to make it utilized completely, I have made a little change by introducing a counter variable. Now, with the help of this, I can able to utilize the buffer completely. Right? Now, come into this part. Okay, counter, decrement and increment. It is nothing but counter equal to counter plus 1, and this counter minus minus is nothing but counter equal to counter minus 1. Right? And during the course of execution, the CPU or the execution unit is not going to do the way we write. Anyhow, this will be converted into machine understandable form and the primitive form, because each and every instruction is going to be converted into assembly code and object code. So after conversion, this instead of counter, the CPU will use register, because the execution unit do not have any idea about what is variable is. And variable, this functions, the printout statement, output statement is all for the purpose of to make the programming language easy for us, so that we will able to easily write code. And a compiler comes and the compiler will do the conversion of our higher level language into lower level language, and the lower level programming language can be executed with execution unit. So now let you consider register 1 equal to counter and R1 equal to R1 plus 1 and counter equal to R1. So this will be the code which needs to be executed by the execution unit to achieve this task, to complete the task of this line. That is, the execution unit need to increase the value of this counter value by 1. This can be transformed or converted into this form, right, by replacing the variable with the registers. Right, this is a transformed code. Right, so if you see in compiler phases, you can find this kind of register formed code. We call it as a intermediate code, right? So now, very simple, we have stored counter value into register 1 and the register value is increased by 1. Then counter equal to R1. That is, after increment, the R1 is placed into again counter. So that at this point, the counter value is increased. This is how the execution unit executes this code. It is not going to execute the code as it is because it needs to be converted, right? For the purpose of understandability, we are doing this form, right? But in the execution unit, this line will be transformed into this form and this will be executed by the processor, right? Execution unit. Same way, let you assume R2, okay? And this counter at this, for this program, counter and R2 will be decremented by 1 in this form, right? R2 equal to counter and R2 equal to R minus 1, and again the value of updated value of register 2 is copied back to counter, so that a decremented value will be found. Now, hope you remember we have used fork, right? So in fork you found that the same copy of programmers made one more cloning, that is copy of an one more process, and both have executed at the same time. Now let you assume these two are the two different process, a process 1 and a process 2, and both are executing at the same time. And the point what you have to note is that both of this process or the functions are utilizing a common space called counter. The counter variable for both of this function or the process is same. It is not a two different copy. And the buffer, right, it is shared. So for both of this code or the process, counter and buffer are shared space, right? By which it knows, say, even if it has produced, and this will know that because this is going to increase the value of a counter as soon as a new item is produced and placed in the buffer. Now, if the execution comes here, the value whatever is reflected here is encountered here because we are using the same counter, so that it understand even if it is incremented here, that will reflect in this counter too, which means that the counter where I have written here and this one all are the same variable, right? Now we know that during the course of execution, this process may be executed at half, and again the opportunity may be given to another process, right? So in such case, because we know due to time overrun, or either it may be for some other priority basis, in any manner, the process will be executed half and which will be put back into the ready queue so that it can wait for later chance, right? And as soon as it gets an opportunity, it can be get executed. So in this situation, that kind of situation, let you assume for execution of this counter plus plus and counter minus minus, right? Now let you assume the producer is busy in producing an item, and it has produced and it has placed an item in the buffer, but it is trying to execute counterpart, right? Now the same way, consumer have consumed some item, right? And it is trying to decrement the counter value. Now what happens? Let you assume now the counter value is 3, right? At this moment 3, as it have produced a new item and it is placed and it is trying to make the counter value as a +1 so that it will become 4, right? And now here the counter is 3, right? And it has consumed an item and it wanted to decrease, which means that as it have consumed and current value of counter is 3, so it just wanted to decrease it to 2, right? But at this moment it is 3. It is trying to decrease it, right? So in this situation, let you assume R1 is 3 and R1 become 4, right? At this point, this process is resumed and opportunity is given to this process. Now, the counter value is copied into R2, right? Still the value of counter is 3, right? So the counter is 3 and it is copied into R2 and this become 2. This become 2. Now, this process is made into waiting and this has got an opportunity to execute. Now, what happens? This is going to place R1 into counter. What is the value of R1? It is 4. So now here counter become 4. R1 is copied into counter. Where R1 value is 4, so it has copied. Yes, it is 4. Now R2 has to be copied into counter because we have left here. Now this process is resumed. So now R2 is copied back into counter. Now 2 will be. So the counter become 2 here, right? And as well here too, because the final update of the counter variable is this, right? Because R2 need to be copied into counter. So now this is the final update of the counter. So now the counter become 2. Is this correct? We do have how many items? Though it have consumed 1 item, earlier it was 3 and it is trying to make it 4, right? And it have made 4, right? So total number of items in this buffer is 3, but due to the consumer is tried to reduce the item and it has reduced it, it become 2 and it is giving a wrong value. Though it have 3 items, but it is updating the counter value as a 2. This problem is called as race condition. And do you understand why this race condition occurred? Because we allowed this process to share a counter variable, right? And we haven't made any constraint. What kind of constraint would make this situation safer? If this process is trying to access counter variable, then no other process should allow. Say if it is trying to update, then this should wait for it, right? And only after completion of this task, and then the consumer should be allowed. But what happens here? Due to the cooperation capability, this can share the counter variable and both of this process or the functions have gone to update the counter value at the same time. So due to which a wrong data or the counter is updated with the wrong value. And this situation is called race condition. So to avoid this race condition, what we have to do is, if the execution have entered into updating the value of counter variable, and because it has entered into this point to update the value of counter, now this has to be informed some process is trying to update the value of a counter. So if this particular program is trying to update the value of a counter, this need to be intimated, wait unless the other process had to complete its updation. As soon as it has completed the another process, which means that if it is a shared variable, ultimately only one program can take control or can go for to update it. And even if it is half done, it is yet not completed, if this process have gone into waiting mode, and even in that situation the other program should not be allowed and other program should wait for this event to occur. Do you remember that I have used the same word the process may gone into waiting mode, right, to some event to occur. So this is the situation where you can find that this has to be kept in waiting mode until this process completes, right? Is that clear? Race condition, it is an example for race condition as well. The purpose of discussing this producer consumer problem is to understand what is race condition is, and what if we allowed more than one process to share a common variable. If you do so, such a kind of error may occur. So to avoid it, we need to introduce some flag variables. There are various strategies followed. Let's see, those strategies will help us to save such errors.